A spacecraft launched in 1977 is now traveling through the darkness between the stars, and NASA is doing everything possible to keep it alive. The biggest problem is distance. A command sent from Earth takes nearly a full day to reach Voyager 1, and another day can pass before engineers know whether the spacecraft received it successfully. Voyager 1 was launched on September 5, 1977. After flying past Jupiter in 1979 and Saturn in 1980, it continued outward with no destination to reach and no planned return. The spacecraft was originally designed for a mission lasting only a few years. Nearly 5 decades later, it is still communicating with Earth. In 2012, Voyager 1 crossed the Heliopause, the outer boundary of the Sun's protective bubble. It became the first human-made spacecraft to enter interstellar space. Since then, it has been measuring an environment that no other human-built instrument has directly explored. There are no solar panels powering Voyager at that distance. Instead, the spacecraft depends on 3 radioisotope thermoelectric generators, or RTGs. They produce electricity from the heat released as plutonium-238 slowly decays. Those generators were producing roughly 470 watts when Voyager launched. Their output has been declining ever since. Every year, a little less electrical power is available, forcing engineers to make difficult decisions about which systems can remain active. The mission team has been preparing for this problem for decades. Instruments have been switched off one after another, not because they stopped working, but because the spacecraft simply cannot afford to power everything anymore. That makes every shutdown significant. In 2025, NASA turned off Voyager 1's cosmic ray subsystem to conserve energy. The instrument had spent decades studying high-energy particles arriving from the Sun and from the wider galaxy. Switching it off permanently meant losing one of the spacecraft's unique scientific capabilities. Then came another serious warning. During a routine spacecraft maneuver, Voyager 1's electrical voltage dropped unexpectedly. The spacecraft came dangerously close to activating its automatic undervoltage protection system. If that system had triggered, it could have shut down equipment without following the carefully planned sequence created by engineers on Earth. For a spacecraft more than 15 billion miles away, recovering from an unexpected shutdown would be extremely difficult. The team managed to avoid that outcome, but the incident made one thing clear: Voyager's remaining power margin was becoming extremely small. In 2026, NASA made another difficult decision. Engineers sent a command to shut down the low-energy charged particles experiment, an instrument that had operated for almost the entire life of the spacecraft. Its internal mechanism had completed millions of steps over decades. Even after its supplemental heater was switched off to conserve energy, the instrument continued functioning in temperatures around -62°C. Eventually, however, the power budget became more important than keeping the instrument alive. After that shutdown, Voyager 1 was left with only 2 active science instruments: its magnetometer and plasma wave subsystem. One measures magnetic fields in interstellar space, while the other can detect waves in the surrounding plasma and help scientists study the density of the gas between the stars. 7 of Voyager 1's original 10 science instruments are now inactive. But NASA is not simply waiting for the spacecraft to die. Engineers have been developing a complicated power-saving procedure known as the Big Bang. The idea is to reorganize the spacecraft's power system by shutting down selected equipment while activating lower power alternatives and carefully managing heaters. That sounds simple until you remember that Voyager was built almost half a century ago. The spacecraft was never designed to operate under today's extremely limited power conditions. Every component that is turned off can also change the spacecraft's thermal environment. Some equipment produces heat that helps keep other systems warm. In deep space, that matters. If the wrong components become too cold, fuel lines and other critical hardware could be affected. If the spacecraft eventually loses the ability to control its orientation, its antenna could drift away from Earth. Once that happens, communication could be lost permanently. So the engineers have to balance electricity and temperature at the same time. Because the command takes almost a day to reach Voyager 1, there is no possibility of real-time control. Engineers send instructions, wait, analyze the response, and then decide what to do next. NASA therefore tested the new power-saving strategy on Voyager 2 first. Voyager 2 followed a different route through the solar system, visiting Jupiter, Saturn, Uranus, and Neptune before continuing outward. It entered interstellar space in 2018 and is now billions of miles closer to Earth than Voyager 1. Its power situation is similar. Several instruments have already been shut down, and the remaining systems are competing for a shrinking supply of electricity. Engineers carefully designed the Big Bang procedure for Voyager 2, including changes involving heaters and other spacecraft systems. The goal was to reduce power consumption without allowing critical hardware to become dangerously cold. The test was successful. That result is extremely important because Voyager the 1st of May now received the same treatment. NASA has been carrying out additional checks before attempting the procedure on Voyager 1. Engineers first need to confirm that the spacecraft's electrical system can handle the change. They also need to make sure the thermal conditions remain safe. If those tests succeed, the Big Bang procedure could give Voyager 1 additional operating time. There is even a possibility that the recently shut down charged particle instrument could eventually be restored if enough power becomes available. That would be an extraordinary outcome. An instrument that had been deliberately switched off to save energy could potentially return to scientific operations. But the reason NASA is fighting so hard to keep Voyager alive goes far beyond the spacecraft itself. Voyager 1 is providing measurements from a region of space that cannot currently be reached by another spacecraft. When it crossed the Heliopause, it began collecting direct measurements of the interstellar environment. Scientists could suddenly study plasma, magnetic fields, and energetic particles outside the Sun's immediate influence. The data challenged and refined existing models of the region. Voyager's measurements showed that the boundary between the heliosphere and interstellar space is far more complicated than a simple dividing line. Waves and disturbances generated near the Sun can travel outward and influence the surrounding interstellar plasma. Voyager has also helped scientists study cosmic rays. Being outside the heliosphere gives the spacecraft a unique position for observing energetic particles that are affected by the solar wind before they reach instruments inside the solar system. Every instrument that is switched off permanently closes another scientific window. There is currently no replacement spacecraft sitting nearby waiting to take over. That is what makes Voyager's declining power so important. The spacecraft is also pushing the limits of communication technology. NASA's Deep Space Network has to detect an incredibly faint signal traveling across billions of miles. Large ground antennas are required just to communicate with a spacecraft whose transmitter is far weaker than modern equipment. At this distance, patience is part of the mission. A command cannot simply be sent and immediately confirmed. Engineers may have to wait nearly 2 days for a complete round trip. And Voyager continues moving farther away. Its velocity is roughly 38,000 miles per hour, but even that enormous speed becomes almost meaningless when compared with interstellar distances. The nearest star system to our Sun, Proxima Centauri, is about 4.24 light-years away. At Voyager 1's current speed, reaching it would take tens of thousands of years. Voyager is not traveling toward another star. It is simply continuing outward. Eventually, NASA will no longer be able to communicate with it. The spacecraft's signal will become too faint for the Deep Space Network to detect, while its remaining power sources will continue declining. But the spacecraft itself will not stop. Long after its instruments become silent, Voyager 1 will continue drifting through the galaxy.